So today in this presentation, we're going to explain the importance and evolution of the technology of wet blasting and how that can be used to control blast media concentration and the removal of spent blast media. I'll talk us through some of the challenges we see, the wet blast technology itself, why abrasive is important to that technology, and how it can be controlled to improve product quality. In tooling manufacturing, we are often presented with several challenges. We believe there are four areas that these companies focus on: the substrate material that's being used, the macro geometries that come from pressing or grinding, the edge preparation, which is achieved, among others, by wet blasting, and then the coating of those tools after edge preparation. For manufacturers to stay ahead of the competition, it's important to have control of all of these areas. However, what we're seeing is the edge preparation seems to have the least levels of investment, but can actually provide the most competitive advantage. Our process, wet blasting, can be used for edge honing, peening, cleaning, and the selection of the abrasive used to deliver that process is critical for its success. The technology itself will be shown in this animation, and it's typically a cabinet-based process and was developed in 1946 by Ryan Ashworth, my great-grandfather. We've been working with tooling manufacturers since the 1980s, and it's often a preferred choice of technology where quality and consistent edges are required. As you can see, there are several variables. The two most critical for tooling manufacturers are air, which has the biggest impact and is easiest to control, and then the specification of the abrasive, which is the second most important factor, but also the hardest to control and measure. The applications are, as mentioned, are for edge honing, pre-treatment and post-treatment, and it can be used on a range of tools from indexable inserts to solid carbide pieces. It's a popular technology and can be because of the versatility it gives and the generally superior finishes we find on pre-treatments and also on post-treatments. These benefits can only be realized if and when the correct abrasive is being used. And in order to do that, we have to understand the shape, the size, hardness, and density of the particles that are going into the machines. Failure to get the abrasive correct can lead to much wider tolerances on the parts and slower processes, ultimately leading to poorer quality tools. The first area of specification is the shape of particle that will be used. This determines the action on the surface being blasted, and for example in the carbide tooling, this is primarily an angular particle because it gives good cutting advantages, which is particularly interesting for honing where we want to grind the shape. Spherical or circular particles can also be used on the left, and those are particularly good where peening or polishing is used. And some customers might choose this where they're looking to impart a compressive stress onto the surface of a coating. There's a third type, which is more amorphous or random in shape, and these particles can be used for gentle scrubbing and cleaning of surfaces that are uncommon in the tooling industry. Following shape is then size, and as the image shows, there's lots of ways to determine the size of a particle. It can become very complicated. Fortunately, within Europe, we benefit from the standards of FIPA, which is a standard body that determines how big particles should be. This allows manufacturers to make a quality selection that is standard regardless of all the different parameters. This can be expressed as a mesh size based on the sieve that it's passed through, or in a millimeter or micron size. Our process, wet blasting, can be used with particles from 36 mesh or 500 microns in size to something as small as 1000 mesh, where the particles are about 5 micrometers in size. The coarser the particle, the bigger the particle, the faster the process. The smaller the particle, the smoother the process, and nicer the results. In the past, it had become common to use mixtures of sizes, for example, a 180/220 mesh or a 220/240 mesh. However, the shift is moving back to one size only because that's giving a better consistency of processing. It is common for tooling manufacturers to focus on something maybe around 150 or 220 mesh for edge honing, and perhaps 320 or 400 mesh for post-treatments. After size, we can also think about hardness when specifying abrasive. It's less of a common consideration in carbide tooling because most users are going to be using a corund or aluminium oxide. Aluminium oxide is both technically and commercially attractive because it gives a really nice balance in terms of cost and durability for the process. Where hardness can be a consideration is when users are looking to increase the intensity of the process or better understand how it will behave and break down while being used within a blasting process. The fourth and final consideration when looking at abrasive for wet blasting is density. It's not widely thought of by users, but density can unlock a competitive advantage for users because it has a real strong impact on the consistency and intensity of the process. It's expressed by us in kilograms per cubic meter, and therefore a more dense abrasive such as stainless steel or steel can provide much more intensity in the blasting. It does benefit those who are looking to do lots of peening or putting stress into a part that helps increase the life, but it also brings its own challenges when used in wet blasting, particularly with the stirring and mixing of this slurry where we need to deliver a very dense solution to the blast guns. To manage this, we have to have good understanding of how the particles behave and how they settle within a liquid, as the difference can be as much as 50 to 70% in settling speeds. Once we've specified the abrasive, the size, the shape, the density, and the hardness, we're then able to make this a commodity purchase thanks to the FIPA standards that we talked about earlier. When we have a bag of FIPA-approved abrasive, we then have a consistent distribution for each particular size, as shown in the bell curves here. For the purpose of tooling manufacturers, this is normally going to be a white or pink aluminium or corund, and I've shown three common sizes that are used by them when they are talking about wet blasting. With a well-managed wet blast process with the correct abrasive, the tolerances on edge honing can be plus or minus 5 microns for inserts, and plus or minus 2 microns when we are talking about solid tools, drills, mills, taps. However, once the fresh abrasive is in the machine, it begins to break down, and our bell curve and distribution becomes wider. The breakdown rate is somewhere between 100 and 500 grams per blast gun per hour. So there is a requirement to manage this and be able to remove the broken media as it is wearing down. Failure to do this can result in a much slower process or a process that is unable to deliver the results required for the edge honing or the pre and post treatments. In some cases, this is managed by heavy maintenance and lots of cleaning, or as the next part of the talk will provide us information on how this can be done through machine design. The first bit in managing abrasive is the mixing. This is where the water and the abrasive are combined to form a slurry. A poorly mixed slurry means the good particles that are doing the work will not be picked up and delivered to the nozzles and onto the surface that we want to hone or clean. To do this well, we look at the heart of the system where we have the slurry pump shown on the right here. And this has two jobs. The first job is to make the mixture, and the second job is to deliver it to the blast guns. Ideally, this pump will be mounted at 45 degrees, and the inlet will be no lower than the top of the abrasive once it has settled. This is to reduce blockages and to allow for quick pickup of the media after a shutdown or a weekend where the machine is not being used. The inlet itself should then be designed to have mesh in there to protect any foreign objects or debris entering the system. This could be stray inserts that have fallen out or other bits that have been dropped into the sump. To help the mixing, you can use either air jets to create a bubbling effect, or in our case, we provide a stirrer shoe which sits directly opposite the pump, allowing this good, well-mixed abrasive and water to be forced directly into the pump inlet. Once the abrasive has been mixed and the slurry is formed, we need to deliver this to the blast guns. This is done in a way that is even and symmetrical, so every time there is a break in the slurry through a Y-splitter or a junction, we are not losing pressure or quantity of abrasive going to the blast guns. The ultimate aim of the delivery system is to ensure that the slurry reaching the nozzle is of the same quality and consistency that it was when it was first mixed in the sump. If we are unable to do this, we get inconsistent blasting, where different guns can have different amounts of slurry and different quality of particles coming out of it. That's particularly important if we want a tight tolerance, where we can have different sizes appearing on the same tool just because of the slurry that has come out of the nozzle pointed at that part of the tool. The guns themselves also need to be considered, and the wear rates and the angles and the pressures will have an impact on the hone. So, for example, a 60-degree blast angle is faster, but affects the K factors should you be looking to specify different ones there. Once we have understood how to mix and deliver the slurry, we then also need to understand how to remove the slurry as it breaks down, primarily through impact with the carbide tools being blasted. Understanding how to do this makes sure that the process remains fast and the tolerance is tight. To do this, we need to talk about separation, and there are many ways to separate the media, and it can be from something very simple or to very complex systems. And again, this will be determined on the type of particles specified at the start. On some machines, this can be the case of just emptying the whole system, but on others, we can put in systems to allow ongoing and continuous production for extended periods. At the core of any separation is an understanding of Stokes' law, which is understanding how particles settle within a fluid and their individual velocities. To understand how to use Stokes' law, wet blast users need to understand the size, shape, and density of the particles they have put in the machine. And there are three main ways to do this. The first is through a patented technology called elutriation, and you see here an elutriation tower which is used to help with this. This is the most controlled and configured way to remove broken particles, and the flow rates of the slurry are slowed down through different orifice plates at the top and the bottom of the tower. This gives very, very tight tolerance on the abrasive, which results in much tighter tolerances on the blasting. The way this works is to bring in some slurry here where it is very turbulent and very chaotic, and gradually with time the slurry slows down and is controlled and diverted through a series of settling tubes. In these tubes, the slurry is travelling much slower than it was originally, and it's that slow slurry that allows the smaller, lighter and broken particles to continue upwards and out of the system. The next technology is more commonly available, and this is through hydrocyclones, often used in mining and minerals, but can also be deployed in wet blasting systems. The cyclones effectively work by spinning the slurry in the cyclonic body, and it is that spinning action that forces the smaller, lighter and broken particles to the outside of the cyclone. As they work their way to the outside, they are then gradually working their way upwards and out, with the good, heavy and usable particles dropping out faster than the rate at which the small ones are leaving. Finally, And regardless of if you've used elutriation or cyclones, there will be an external separation tank where the media is further controlled. In this case, we can offer a series of settling tanks in a weir system, and it's that weir system which further slows down the slurry, giving the broken particles more time to fall out and into the buckets provided. What this means is we've then got a very easy to clean system, and the resultant slurry coming out at the end of the tanks is very clean and mostly free of abrasive, allowing it to be returned back into the system as a closed loop design, and often is used for rinsing of components after blasting. And here we have some live examples of the elutriation tower, a hydrocyclone, and some settling tanks in a weir system. Finally, and to balance the process, once we've understood how to mix, deliver, and separate, we must think about monitoring. And this can be done automatically or manually, and systems can be put in place to alert users how much abrasive is in the system. If the separation is working well, and there's only good abrasive in the machine, to achieve optimum results, we're looking for a ratio of about 15 to 20% concentration of abrasive to water in the slurry. If we have too little abrasive, the process becomes very slow and ineffective. But if we have too much abrasive, you risk blockages in the system, which create maintenance problems and inconsistency of processing. The manual way to do this is with a sight glass, and it's recommended this is done every 30 to 60 minutes, just to check where the level is done. This is where a sample of slurry is taken out of the machine into a calibrated tube and allowed to settle. Once it has settled, we can see where it sits through the calibration of the tube, and it gives a rough indication of what percentage of abrasive is in the machine. Automatic monitoring, as shown in the picture here, can be done intermittently, as with the manual process, or it can be done continuously. Continuous monitoring allows us to react more quickly, and for producers of high volume continuous production, this is of benefit because the machine can react much quicker before several hundreds, or in some cases thousands of parts have been produced with the incorrect slurry concentration. In terms of systems design, we are then able to tie that all together as the process and instrumentation diagram shows here, and you can see how this works as a whole system. So we start here with the pump and the mixing. This then delivers it to the blast guns, and at the same time this is happening, we are going through some hydrocyclones, some settling tanks, before it returns back into the sump, creating this closed loop. We can also see on the design here where the monitoring system fits in, and when specified, you can also look at the rinsing for cleaning of the parts after the blasting. I'd like to thank you all for listening, and in conclusion, we can see that the specification of abrasive for honing, cleaning and peening is vitally important for users wanting to take good control of their manufacturing processes. Having selected the right size of abrasive, it then becomes necessary that any wet blast system that is specified has the correct deployment of mixing, separating and monitoring systems. Being able to do this correctly will unlock competitive advantage, and it will give you better quality honing and pre and post treatments. If you'd like to discuss anything further, we're in Hall 3, stand 3111, and you can see one of our machines and talk about any specific questions you may have. Thank you.